Hello again. This is going to give you some highlights about 8.3. I'm going to go through this one in a little bit more detail than I did 8.1 and 8.2, seeing how this is new content. Good news is that because we have a general idea of what a confidence interval is, this one is just more specific to a population mean. So naturally, we have a different formula because our numbers mean different things. Remember in chapter 9, when we were looking at hypothesis tests for means, we had to think about using a t-distribution, and that was because we didn't know population standard deviation. So the standard deviation of our sampling distribution we would calculate by doing sigma over square root of n. But remember, we don't know sigma, so we're going to use sample standard deviation in its place. We refer to that as standard error, and when we use that to estimate standard deviation, we have to use a t-distribution instead of a normal distribution. So we're going to see that t-distribution come back again with confidence intervals for means, but let's go ahead and look at our formula for constructing a confidence interval for a population mean. So again, I wrote out in words our general formula, our sample statistic plus or minus our margin of error. Remember, all of this is our margin of error, made up of our critical value times our standard error. Remember that critical value we find based on our confidence level, and that critical value is saying how many standard deviations we need to go out from the mean, from the center of the distribution, in order to capture a certain percent of the observations. So we talked about that first when we were looking at the critical value Z star in 8.2, and we thought first about the empirical rule. Remember, we know from the empirical rule that within one standard deviation of the mean, there should be about 68% of the observations. Within two standard deviations of the mean, there should be about 95% of the observations. And within three standard deviations of the mean, there should be about 99.7% of the observations. So we used that to kind of build on our Z-star critical values in 8.2. We'll do the same thing, but now we're looking at T critical value. So the 68, 95, 99.7, remember, only applies to normal distributions. So we do have to figure out different critical values when we're using the T distribution. So our sample statistic here, because we're trying to estimate a population mean, our single best guess is going to be a sample mean, or X bar. So here again, we're going to use a T star critical value from a T distribution. And then our standard error, as noted before, is going to be our sample standard deviation divided by the square root of our sample size. Of course, anytime we do an inference procedure, we want to make sure we check certain conditions. Again, good news, these three conditions here are the same ones that we used in hypothesis tests for a population mean. So we do have to check our sample size is large enough. Remember, we do have three things here, or three different ways to check this one condition. So the first way we can check is to make sure that our population distribution is known to be normal. Generally speaking, we don't usually know that information. If we did, great, we could move on. However, this one is one that we commonly can use. So if we don't know anything about the population distribution being normal, if our sample size is at least 30, then we can in fact use the T distribution to model our data. Now, of course, we do have that one little caveat. If we don't know this and our sample size is actually less than 30, then we can look at a graph of the sample data, whether it's a histogram or a dot plot, but of our sample data, meaning if you only have 22 observations, you want to look at a graph of those 22 observations. And if that graph, or if that sample data distribution is roughly bell-shaped with no outliers, then we can assume that that sample came from a population that was normal. Therefore, we can use the T distribution with a certain number of degrees of freedom. Of course, we have our random condition and then our independence condition as well. So before we get into an example using that formula, I wanted to again talk about how to find a critical value. So referring back to 8.2, we found a z-star critical value using a normal distribution. Now we're going to find a t-star critical value using a t-distribution. Remember, t-distributions depend on degrees of freedom. So notice in each of these examples, you're given the sample size. So in that first one, let's just look at the first one together. That first one is a 90% confidence interval, and we know that our sample size is 124. So I'm going to go over to StatCrunch. So we're going to pull our T calculator from the Stat menu, Calculators, T. And because we know our sample size was 124, our degrees of freedom will be 123. And we wanted a 90% confidence interval. Oops, I should be on the between. So we have our degrees of freedom at 123. We want to know how far do we need to go from the center to capture 90% of the observation. So I'm going to type in 0.9. And I'm going to ask StatCrunch to calculate what that T critical value is. So that middle portion, that red portion there is 0.9 or 90%. And we would need to go 1.6573 standard deviations or standard errors from that center in order for that red portion to be 0.9 or 90%. So our T-star critical value is going to be 1.6573. I did draw a little picture, but I wanted to show you how we get that in StatCrunch as well. So note to self, you saw that I didn't do it at the very beginning, but note to self, you always want to make sure you're clicking on that between button first. It's pretty easy to forget that, but you always want to think about how far do I have to go from the center on each side, symmetric to the center. So you're really looking at the middle 90%, not the left 90% or the right 90%. So feel free to check out B and C on your own. I drew the picture here, but make sure that you can type that into StatCrunch and get these same T-star critical values that we have here. So, of course, we have a nice example for us to run through. I am going to go through this one in some detail and then probably let you guys try 18 on your own. Number 17 is talking about the time it takes, or excuse me, not the time it takes, the number of squares of toilet paper it takes to absorb a 1/4 cup of water. So these students randomly selected 18 rolls of generic brand toilet paper. And here we actually have our sample data. So this 29 means from the first roll of their random sample, it took 29 squares to soak up that water. In our second roll that was randomly selected, it took 20 squares to soak up that water, so on and so forth. So we actually have the results from our 18 rolls. We also have a histogram of these 18 numbers. So this right here is representing our sample, not the population, not the sampling distribution, but just these 18 numbers here from this sample. These summary statistics are also referring to just that sample. We know that because this says 18, n equals 18, that's our sample size. So this mean here is really just X bar. Our standard deviation is our sample standard deviation, which is just S. Then we have the 5-number summary in case we wanted to use that. For this problem, we won't, but this is just computer output, I think, from StatCrunch, and all of those things are usually included. So here we have our prompt. We want to construct a 99% confidence interval for the true mean number of squares of generic toilet paper that it takes to absorb a 1/4 cup of water. So part A, checking our conditions for constructing our confidence interval. So if we flip back here, we're going to check these 3 things in no particular order. So we do know that it was a random sample of 18 rolls of toilet paper. It is reasonable to assume that the number of squares it takes in one randomly selected roll doesn't tell us anything about the number of squares it takes from another randomly selected roll. So we can go ahead and check that guy off. Now this one here, let's kind of talk about this one in more detail. So if we wanted to check that the population distribution is known to be normal, we would have to know we would have to know information about every single roll of this generic brand of toilet paper and how many squares it takes for every single one of those rolls. And we would need to know that all of those numbers for all of those rolls makes a normal distribution. We don't know that information, obviously. So we could go to our next check, which would be n is greater than or equal to 30. Well, it's clearly not. 18 is not bigger than 30. So here, this is why this is given to us. Or we could be told, you know, the data distribution, the sample data distribution looks approximately bell-shaped with no outliers. But we are given this graph here because 18 is smaller than 30. So yes, I know this doesn't look perfect, but it does look roughly bell-shaped and there don't appear to be any outliers. So it is okay to assume that these 18 values here came from a population that was approximately normal. So we're going to go ahead and check that condition off. So now let's actually construct our confidence interval and then we'll interpret it as well. So I wrote out our formula here. So our X bar is our sample mean and we can get that information from our table here, 24.9 for repeating. Plus or minus our T-star critical value, we'll look at that in StatCrunch in just a moment, times our standard error. So again, S is our sample standard deviation. That's given here in our summary statistics. We know that our sample size was 18. So here we've got our standard error. Let's take a second and look back at StatCrunch and figure out how we get that 2.8982. So two things we need in order to figure this out. We need our confidence level, so 99%, and we also need our degrees of freedom. So remember our sample size was 18, so our degrees of freedom will be 17. And then we want a 99% confidence level. And there we go. So again, here our critical value is 2.8982. So we've got our 2.8982. I do encourage you to check to make sure you can calculate that in your calculator. Whatever calculator you're using, whether it's a scientific calculator, a graphing calculator, a Desmos app, or something like that, just make sure that you are checking to make sure that you know how to type this in your calculator with its conventions and get this answer here. Remember, to interpret our confidence interval, we want to include three main parts. Our confidence level, so how confident are we? And you know what? I'm just now noticing that that is not correct. This should say we are 99% confident. I will also change that on the key on ELC. So we are actually 99% confident that the interval from our low bound to our high bound captures what it is we're trying to estimate. Remember, we're trying to estimate the true mean number of squares of generic toilet paper needed to absorb a 1/4 cup of water, but we're just making an inference based on these 18 values that we got. So we are making a guess at the true mean number of squares of generic toilet paper that it takes. So we want to make sure that we include that information in our interpretation. I am going to let you guys try 18 on your own. I would try to actually go through, work through it, maybe pull up the blank notes and try to work through 18 on a separate sheet of paper or print it off, and then go back and check your answers against mine. And then, of course, there are some extra practice for 8.3 that you are welcome to try. Again, I would encourage you to try these on a separate sheet of paper and then go back and compare your answers. I hope you guys are doing well and staying healthy.